Yes, Math 6500. What this video is going to be all about is just going to summarize. So it's going to present a summary of tests concerning regression coefficients. And actually, I'll keep an eye on the clock here, but actually I'd say this is probably going to be the next two videos. I don't know how long it's going to take me to get through this one. Guys, this video is going to be, well, actually the next two videos are going to be more theory than actually application. And darn, I forgot to include a song. Shoot. Well, after Wobble, I'd say you guys are maybe glad that I did include a song. Sorry about that. Also, keep me posted on what you guys like best. The white, over, where I write on the sheet of paper, or whether you like this. I'm really struggling with which one I like best. So I guess that means I have a pretty darn good life if that's what I'm spending my time thinking about. So anyway, as you can see, I'm doing the blackboard here. Guys, we've seen so far examples when eliminating one and two variables from a three predictor model. And using R, it's really, really, really easy to to make these calculations. Well, as you might imagine, mathematics is all about making generalizations. So, as you'd expect. This is a process that can be generalized. Which is precisely the intent of this video. Now let's revisit 5500. And back in 5500, we looked at the overall f-test. To test if there's a regression relation between y and a set of, let's call it k predictors. So, we have x1, x2. Well, I guess just really we should just go x1 because k could be 2. Up to x sub k. And we saw that the process back in 5500 was, to use the ANOVA for regression technique. And let me be thorough here. And we would test the null hypothesis. That all of the predictors were equal to 0. against the alternative, not all of the betas, up to k equals 0. And, we should be pretty good at that. And guys, just for the sake of being thorough, we saw that the calculation was the sum of squares for the regression over its degrees of freedom divided by the sum of squares error divided by its degrees of freedom, leading us to the mean square regression over, of course, the mean square error. Now, in terminology that we're currently using, this, again, has 4 components. Our degrees of freedom here would be the number of predictors. Our degrees of freedom in the denominator would be n minus k plus 1. We have to add 1 to it to account for beta 0, which had been estimated and is used in the calculation of sum of squares error. But at the end of the day, we just look at the sum of squares regression for the full model over the sum of squares error, as we always do for the full model. This F star follows the F distribution with degrees of freedom k n minus k plus 1. And it should go without saying, but this value, if it's high, is more supportive of the alternative. And if the F value is low, this will create a higher p-value. So it's more supportive of the null. So again, high test statistics create low p-values. Low p-values are evidence against the null, so more supportive of the alternative. Low F statistics create high p-values, more support for the null hypothesis. Now let's generalize the process if we would like to test the removal of one of our betas. So the null hypothesis would be beta I is equal to 0 versus the alternative beta I, of course, not equal to 0. The F statistic is, as I hope you would know. And let's just pause here. What do you think it would be? Well, let's pull in what we should know. Well, we're adding, looking at the elimination of 1, so our degrees of freedom will be equal to 1. Degrees of freedom for the error, sum squares error, is still n minus k plus 1. We should know that the sum of squares error is always calculated. It looks like an R, doesn't it? Always calculated on the full model. And the sum of squares regression is calculated on the addition of the variable. Well, no, we don't know it's x. I'm getting sloppy here, guys. It's early in the morning, I'll tell you, and I haven't had enough coffee. So it's the addition of adding x sub I when x sub 1, we need to be careful here with the notation. So let's say x sub I minus 1 to x sub I plus 1 up to x sub k. So you'll notice that I intentionally, between these two terms, left out the x of I, because it's obviously the focus of the test. And again, this follows an F distribution with and just like before, a high F statistic. Well, you guys know. Now let's look at the process if we want to test the removal of several betas. And guys, by several, essentially what I mean here is we're going to, well, n is sample size. Okay, let's pretend n changes roles here for a second. And it's the number of betas that we're removing. So this would be 2 or more. So guys, first thing we would want to do is we got to set up some notation. So this is going to be a little wacky at first, but just bear with me. Let's set Q to be the first. Okay, imagine having. Well, I'll tell you what. I think I'll do an example of this. So let's just get the notation down. Okay. So what I want you to think about here is this Q. Let's think about rearranging our betas such that the last betas are up for removal. So, in other words, we could say that the last k plus 1 minus q coefficients are being dropped. And I think what I'll do, I'll run through an example of this. Once we get the theory, and hopefully I can make it make sense for you. So you should know now that the F statistic, and you can probably tell I'm teaching a little different here because this is not really difficult material, but the notation when you first see it gets a little crazy. So guys, we got 4 things here. What do we know for sure? Well, we know for sure that the degrees of freedom for the numerator will be k plus 1 minus q, and we should know that n minus k minus 1 will be the degrees of freedom for sum squares error. Now, we should also know that the sum of squares error is going to always be for the full model. And the sum of squares regression is going to investigate the addition. Well, if we've ordered these betas, I should say we've reordered these betas to start with the qth element. I'll tell you what, I'm going to need more space here. Let me get over here. So I can see where this is headed. So if I have the sum of squares regression for the qth element and the qth plus 1 element all the way up to the k element, which is the very end element, and I've got in my model x sub 1 up to x sub q minus 1. Now this degree of freedom is kind of bugging me. Let me think this one through. So k plus 1 minus q. Yeah, okay, that's cool. So guys, from this, this should show us that the mean square regression is going to be calculated on the addition, given everything else. I think I've learned one thing. Don't put up videos until you've had your coffee. Any other coffee freaks out there? All right. And of course, the mean square error is on the full model. All right. Now, I think it's going to be probably good to run through an example of what I mean by this. And if that theory there just made complete and utter sense to you, then you can, turn off the video and do something else. But let's look at a model. Let's say that we're trying to we're investigating a full model of y sub I equals beta 0 plus beta 1 xi1 plus beta 2 xi2 plus beta 3 xi3 plus beta 4 xi4. How far guys do you want to go? Well, since we're running out of space, let's say the full model has 5 predictors: beta 1, beta 2, beta 3, up to beta 5. We want to investigate dropping beta 1 and beta 4. Now guys, the initial ordering, obvious. But rearranging the order of the betas or the variables clearly is not an issue. Now you might say, well, some of the calculations are, but when we're investigating the removal of a couple, it doesn't matter where they fall in the beta 0, beta 1, beta 2, beta 3, beta 4. So we're going to reposition. So I still want beta 0, but guys, remember, beta 1 and beta 4 need to come at the end because they're the ones to be removed. So I'm going to have beta 2, beta 3, and beta 5. So guys, in the new ordering, this will stay my beta 0. This is beta 1. And out here becomes beta 5. So beta 1 becomes beta 4, beta 4 becomes beta 5, and so on and so forth. Now, this Q starts where we are removing. So guys, our Q in this case is equal to 4, because those are the variables that we're investigating dropping. So guys, Q is equal to 4, and we have a 5 predictor model, so K is equal to 5. Now, hopefully that makes sense. So guys, we're going to test the alternative. So both of these aren't necessarily equal to 0. So guys, the F statistic here, again, 4 parts. Now guys, remember the degrees of freedom for the denominators n minus k minus 1. So we have, 5 predictors. So our degrees of freedom would be n minus 6. And that makes sense, right? I mean, it should. I mean, we have 6 degrees of freedom here because including beta 0, which we include in the sum of squares error, we have 6 estimates that we've made. And something else that should be obvious is the sum of squares error is always on the full model. All right, that should be clear. The degrees of freedom for the numerator is k plus 1 minus q. Well, k is 5 predictors, and q turned out to be 4. So if my mental arithmetic is correct, that gives me 6 minus 4, which is equal to 2. So guys, think about it. What did the degrees of freedom for the sum of squares regression always tell us? The number of variables that we were considering dropping from the model, or the number of variables that we were adding to the model to look at the difference of the sum squares for the regression. So guys, we start with x sub q plus 1, but q is equal to 4, all right? Well, we established that, right back here. So already in the model. Okay, now, just following suit with what we've done before, F star is going to follow the F distribution, degrees of freedom 2, n minus 6. And just like before, the high F statistic is evidence against the null hypothesis. All right, let's, okay. Let's, I'll tell you what, that's, I don't really know how far I am into this, but this is really a great place to end this video, so I think I'm going to do that. The next thing we're going to look at are special cases. Let's